In this lesson, we're going to learn about something called one-to-one functions. And we're going to approach this from three different angles. We're going to look at this topic numerically, graphically, and analytically. Now, recall that a function is a relationship between x and y such that each x value corresponds to exactly one y value. In other words, the x values do not repeat. So if the point 2 comma negative 3 is on the graph of a function f of x, then no other point can have an x value of 2. However, it is possible for another point on the graph of f of x to have a y coordinate of negative 3. For example, both 2 comma negative 3 and 5 comma negative 3 would be perfectly acceptable for a function. So in a function, the x values cannot repeat, but the y values can. However, if we make the rules a little more strict, then we introduce something called a one-to-one function. This is a function such that each y value corresponds to exactly one x value. In other words, the y values do not repeat either. For example, if 2 negative 3 and 5 negative 3 are both on the graph of f of x, then there's a y value, namely negative 3, that has more than one x value. Therefore, there is no way that the function f of x is a one-to-one function. So again, at any point during the lesson, if you'd like, just pause the video so that you can take the appropriate notes and then join back so that you can follow along with the explanation. Let's take a look at this little table here. Again, go ahead and pause if you'd like to take down the notes, and then we can discuss this. So, as I mentioned, we're going to look at determining if a function is a one-to-one function numerically, graphically, and analytically. Numerically is when we're simply looking at a table of values. This would be a discrete function when we just are looking at a finite number of points. And we can say that a function, a discrete function, is one-to-one if it has no repeating y values. Now, the fact that it is a function already tells us that the x values don't repeat. So now we are just adding the additional rule that the y values will not repeat either. Now, if you have a continuous function, a curve of points all connected together so that there are infinitely many of them, this would be more difficult to determine. So again, if you can look at your graph and tell that the y values are always increasing or always decreasing, then that's an indication to you that the y values will not repeat. You can imagine that if the y values increase and then decrease, or vice versa, you will definitely have repeating y values. Graphically speaking, if we have the graph of a function, remember the vertical line test that we used to determine if a relation is a function. So now to determine if it is a one-to-one function, then the graph must pass the horizontal line test as well. This means that if you were to draw any horizontal line on the graph, it should not intersect the graph more than once. If so, then it's not a one-to-one function. Analytically, what we will do is we will solve for x and determine if we have a function. And we will discuss this in just a moment. This causes us to introduce really the point of one-to-one functions, and that is to determine what we call the inverse of a function. The inverse of a function is defined to be the function formed by switching the x and y values of the function. What property of the function must exist in order for the inverse of the function to exist, and why? The inverse, which we will denote as f with an exponent of -1 of x, exists if and only if f of x is 1-to-1. Let's think about that for a moment. We know that a function cannot have repeating x values. So for the inverse, if we're about to switch the x and y values, then we want to make sure that those original y values do not repeat either, because those y values are about to become x values of our inverse. Whoops. Again, if you'd like to take a moment to pause the video so that you can do a little note taking and then join us back, please do so at any time. Okay, so if we can determine that the function is indeed 1-to-1, then we can find what we call the inverse of the function. Numerically speaking, to find f inverse, denoted by f with an exponent of -1 of x, we simply switch the domain and range values in the table. So it's simply taking the columns and switching them. Very simple. Graphically, if we want to look at the graph of a function and we have determined that it is indeed a 1-to-1 function, then we can take some special values from the graph and make a table, switch the x and y or domain and range values, plot the new points as a guide to help us draw our inverse. And we'll look at an example of how we will do that in just a moment. Analytically speaking, if we have the function itself, we will simply take f of x and replace it with y, because remember, f of x is just a fancy way of saying y. Then we will switch x and y and solve for our new y. Now that we have solved for our new y, this is our inverse, and we can go back to function notation and replace y with f inverse of x. Let's take a look at some examples. The first two examples are numerical. We simply have a table of values. In the first example, example A, we have a function, and I know it's a function because none of the x values repeat. However, we have y values that are repeating. Notice there are two coordinates, -3, 2, and 5, 2, that have the same y value. Because the y values repeat in example A, f of x is not a 1-to-1 function. This means that the inverse of the function does not exist. Think about if we were to switch our domain and range values. We would have x values that repeat, which would not be a function. And that's why we say that the inverse of f of x does not exist, because we want the inverse of a function to also be a function. And in example A, that would not be the case. In example B, we have a table of values where the x values do not repeat, of course, as is the case with any function. And also the y values do not repeat. So for this discrete function, we are able to find the inverse. We would say that f of x is 1-to-1 because it does not have repeating y values. So we can make a table of values for the inverse, f inverse of x. Notice I've simply switched the domain and range quantities, and this is my new function, which is the inverse of f of x, denoted with a little exponent of a -1, and that is how we indicate inverse in function notation. In the next two examples, we'll look at inverses graphically speaking. In example C, I have a graph. The original graph passes the horizontal line test. If I draw any horizontal line, it will never intersect f of x more than once. So I know that I am able to find the inverse of f of x. So I simply picked out a few points from my original f of x, -5, 5, -2, 1, 2, -1, and 4, -4. I switched my x and y's for my inverse, and I plotted the new points to draw my inverse function. So on the graph in purple, you will find the inverse of f of x. Because the original graph passed the horizontal line test, then I am able, and I put vertical, let me put horizontal here. All functions pass the vertical line test, but f of x is 1-to-1 because it passes the horizontal line test. This means that the inverse does exist. Okay, and I made the same mistake over here on part D. F of x, or excuse me, this is g of x, so let's call it g of x. Fix that. G of x is clearly a function. It passes the vertical line test. However, it fails the horizontal line test. Horizontal. If I draw a horizontal line, say at a y value of 2, it would cross the graph of g of x more than once. This means that the inverse of g of x does not exist. And this is g of x, not f of x. So in order to find the inverse of a graph, first of all, it must pass the horizontal line test. Then you can pick some values on the graph to make a table, switch them, and use that as a guide to draw your inverse. Indeed, it does exist. So for a table of values, switch x and y as long as the y values don't repeat. For a graph, as long as it passes the horizontal line test, make a table, switch the values, and regraph your points. In example E, we see another function that is invertible, we would say. That's how you say it when the inverse exists. So we have this h of x, and it passes the horizontal line test because every horizontal line would cross the graph of h of x no more than once. So I just selected a few points on h of x. -5, -3, -4, 1, -3, 3, and -1, 5. I see that this is not quite -4, 1, but it's close. Then I switched x and y values, and I got -3, -5, 1, -4, 3, -3, and 5, -1. And I used those as a guide to help me draw the inverse of h of x. Once again, I called this f of x, so let me fix that because it is clearly h of x. So let's change that. So h of x is 1-to-1 because it passes the vertical line test, the horizontal line test. Whew. Horizontal. Remember, every function passes the vertical line test, but because this passes the horizontal line test, that means the inverse does exist, and I have found it as well. So let's call it h of x, like it's supposed to be. Let me fix it. I'm so used to functions being called f of x, but they are clearly not always so. All right, so we've looked at finding inverses numerically and graphically. Now let's look at finding inverses analytically. Here's what you do. Remember that f of x is just a fancy way of saying y. So I rewrote the function, but I put y instead of f of x. In the next step, I switched x and y. Now I'm going to solve for y. I added 2 to both sides. I took the square root of both sides. I added 3. So my function, y equals plus or minus the square root of x plus 2 plus 3. This is not going to be one-to-one. There's going to be more than one answer, hence the plus or minus. There's going to be more than one y value for each x value in my original function, which means that the inverse will not be a function at all. And so the inverse of f of x does not exist. And that plus or minus tells me so. If you think about the original f of x, we see that it's a quadratic, which means when you graph it, it would be a parabola. The inverse of a parabola would be a sideways parabola. All right, so that would not be a function. A parabola fails the horizontal line test, so its inverse does not exist. Let's take a look at the next two graphs, or the next two examples. Again, you might want to consider pausing the video, writing down the examples, and then join me back here so that we can talk through these. For example G, I rewrote the function, but I put y instead of f of x. Then I switch x and y. Now the rest of this is solving for y. I want to get y by itself. My next step is to add 3 to both sides. Then, to get rid of the fraction 2/5, I multiply both sides by the reciprocal of 2/5, which is 5/3. I have now isolated y. Y is equal to 5/2 times x plus 3 in parentheses. This is my inverse, f inverse of x. Let's try g of x. I begin by rewriting my function with y instead of g of x, because g of x is just the y value. In the next step, I switch x and y. In place of y, I put x, and in place of x, I put y. Now I will work to isolate my y value. First, I subtract 4 from each side. Then divide by 2. Y is trapped inside of a square root sign, so I square both sides to get rid of my square root. Now I will subtract 3. I've isolated y. Y is equal to the quantity x minus 4 over 2 squared minus 3. And this is my inverse. This should be g of x, not f of x, once again. Funny how I can think of it now. All right, looking good. Next, we'll explore another important aspect of inverses. Once again, if you like, pause, write, then resume. Let's start by finding the inverse of this function g of x. First, I rewrite it, except in place of g of x, I put y, so that in the next step, I can switch x and y. Now I will work to solve for y. The first thing I want to do is get rid of that divided by 2, so I multiply both sides by 2. Then I add 4 to each side, and I'm almost there. I just need to divide both sides by 3. Now y is isolated, and this is the inverse of g. Once again, I put f for some reason. I don't know what I have against g or h. Habits. All right. So the inverse of g is 2x plus 4 over 3. In the next column, we're going to do something very interesting. We're going to find g of g inverse of x. That means we're taking our original function of g, and wherever x is, we're going to put the inverse, g inverse of x. Remember, the inverse was 2x plus 4 divided by 3. So I've taken that quantity and substitute that back into my original g of x in place of x. Well, when I have 2x plus 4 divided by 3 and I multiply by 3, the 3's simply cancel out because times 3 and divided by 3 are opposite operations. Excuse me. And I'm left with 2x plus 4 minus 4, all divided by 2. Of course, plus 4 and minus 4 goes to 0, leaving me with 2x divided by 2, which is x. In the next part, I'm going to do the opposite. I'm going to take the inverse of g of x, 2x plus 4 over 3, and substitute g of x. So remember, my inverse, which I found in the first column, is 2x plus 4 over 3. In place of x, I'm going to put the entire g function, 3x plus 4 over 2. And it looks like this. The 2's cancel, times 2 and divided by 2, leaving me with 3x minus 4 plus 4 all over 3. The minus 4 and the plus 4 go to 0, and I'm left with 3x divided by 3, which is x. This is a very interesting thing that happens when you have a function and its inverse. When you create a composite function of a function with its inverse, either way, you always will get x. It makes perfect sense when you think about what a composition of functions and inverses do. If two functions, f of x and g of x, are inverses of each other, then there are two special composite functions that will equal the same thing. If f of x and g of x are indeed inverses, then f of g of x will always equal x, and g of f of x will always equal x. So in the last examples, it says determine if each of the pairs of functions below are inverse functions of each other or not. And we're going to use this idea to determine that. Again, you might want to pause, write, and resume. In part A, first I will see if these are inverses by substituting the g function inside the f function. So in place of x, I replace it with g of x. When I simplify this and cancel out the 2's and the minus 3 and the plus 3, I end up with just x. That's a good start. Now let me test g of f of x. This means I'm taking the g function, x minus 3 over 2, And in place of x, I'm going to replace it with 2x plus 3. That also simplifies to x. Since f of g of x is equal to x, and g of f of x is equal to x, then yes, f of x and g of x are inverse functions. In example B, I begin by substituting g of x into f of x. So right here where you see the x divided by 2 minus 1, I'm going to put 2x plus 1 where x is. No matter what you do with that, it's not going to equal x. And I could stop right there. But just for the sake of being thorough, I went ahead and showed you what it would look like for g of f of x. This time I'm taking the g function, and in place of x, I'm going to put x divided by 2, and I should have put minus 1. Okay. So I'm taking f of x and replacing it here. Now, when you simplify this, you're not going to get x. And again, that's all we need to know, is that it's not going to equal x. It has to equal x both ways. And this one does not equal x either way. So whatever f of x and g of x are, they're simply not inverses of each other. So you should be able to determine if two functions are inverses. You should be able to find the inverse of a function given a table or a graph or the function itself.